Hey class, Adam Ward here. I want to talk with you today about data quality assessment, quality control, and cleanup. In other words, we have now designed and executed our field experiment, and we've got to sort through the pieces and figure out what to do with the data. So the goal of this video is to help you see the major steps that we go through in my group when we get home with field data. All right, so what I'm going to call step 0, lab analysis if required. If you are a person who has loggers for everything you need, then what you're going to come home with is a pile of data already. If you're a person who is collecting small samples of water to analyze in the lab, maybe for a particular tracer of interest, maybe because it can't be measured by a logger or you don't have access to one, this step is for you. So you will have come home with a series of small bottles of water collected with careful protocols in the field, with documentation of when and where each one was collected and how they have been handled since they were collected. In the most technical step, there is a magic box shown here in purple, and out the other end of this magic box come tabular data, which will have your sample number that you can translate into a date and time, as well as the concentration of whatever analyte or analytes you're sampling for. So what I'm simply saying here is, in order to proceed through this video, we need a concentration time series. If you've collected this on a logger, it probably downloads from the instrument in that form for you. If you've collected this as a series of grab samples, then you've got some work to do in the lab to generate that time series. Okay. With a time series in hand, the next step is to subtract the background concentrations. And so if we are using a tracer that is found naturally, so for example, chloride, of which we will find chloride ions dissolved in every stream that we sample, we want to subtract the background conditions and isolate the signal that was due to the tracer. So how might this look? Here's a set of observed tracer. I'm showing it here in blue circles. So those are the concentration time series you might have, whether they're from a logger or from analysis of water samples. We know when our injection occurred, and what I'd like to do then is look at the data that were collected prior to our injection time. We know for a fact that those samples are not being influenced by our tracer. It wasn't in the system yet. So I've circled them here in orange. Now there are a few strategies for background correction. One strategy that I've seen is to take the average concentration of those background samples and subtract it from each site. And so I'm showing that here in purple. And the idea of doing this is you take the average of, in this case, the points that are circled in orange. That's the average concentration pre-tracer, and you subtract the average. One limitation is you may end up with some tracer values that are less than 0. So the purple arrow that I'm now sort of going around in pink is pointing at one such value. Now what will you do with a negative concentration? You can't have negative grams per cubic meter. So now you've created a problem you have to deal with. Perhaps you assign that a value of 0. Well, that's a choice that you're making and that you'll certainly want to document. An alternative strategy that I've seen is to take the minimum concentration in the background and set that to 0. So, in other words, we take the lowest point in the orange circle and we subtract that concentration from all other points. And again, you create problems for yourself. This means that most of your background observations are not at 0, and your system may never come back to 0. Because you're choosing the lowest point. So background might be slightly above 0 as a long-term average. So neither of those are perfect strategies. I tend to like the first strategy, which is to have collected enough background points that I can get both a mean and a variance of the background conditions, use the mean to adjust, and then we'll take any negative values, and if those are going to cause problems in our analysis, we can consider setting those values to 0 because they're not physically meaningful as negative numbers. Okay. Now, in some cases, you may need to go through a step here where you convert from the proxy that you measured into a concentration. For example, one really common strategy is to use sodium chloride or table salt as a tracer, and rather than measuring it with a chloride probe, we measure fluid conductivity. So salty water is more conductive. And so in this case, what we'll need to do is create a relationship that links the proxy that we measured, conductivity, to the tracer mass that we've added, salt mass added on the y-axis. The idea here is that we would do this optimally using a calibration solution prepared in water from the field site. That's not always possible. Sometimes you've got to use water from your laboratory tap or from a milliQ source or something like that. And most optimally, you would do this before and after the study so you could check for any drift that might have happened in your sensors. We won't go farther down this rabbit hole right now, just to point out that there are some potential complications here. So these data points, all of these purple circles that I'm pointing to here, this is going to come from a series of lab dilutions. Those are not data that were collected in the field. Those are data that are based on taking a known mass of your tracer and dissolving it in a known volume of water, ideally from your field site. So you're making a calibration curve here. And what this lets you do is take the thing that you measured, conductivity, and use that relationship to convert it into a concentration. And that's what I'm trying to depict with the orange arrows on that plot. Okay, we've got a concentration time series in hand. It might look something like this. At this point in the procedure, I think it's important to complete a visual inspection and remove data that are not meaningful because they are potentially outliers or sensor failures. So I'm looking at, for example, these 2 points that I've circled in blue, one creating an outlier that's extremely high and one that's extremely low. My guess would be that these are potentially due to something being stuck in the sensor, to a particulate, like a particle flowing through your sensor or making contact with your sensor, or frankly just some error in the circuit. Now, for my money, if there are a few of these, and I'm typically thinking like 3 or less, I feel quite comfortable essentially saying I'm going to remove those from the data set, right? Based on visual inspection, I've removed a small number of outliers. 2 or 3 outliers, if I have thousands of points from a high frequency data logger, is not too bad. 2 or 3 outliers, if I have 100 grab samples, I'm still willing to do that. 2 or 3 samples, if I have 10 samples in total, makes me question if they're actually outliers, and I think you probably need to revisit some quality control. If these are based on grab samples, and I really want to stress this, if these are based on grab samples, you should hopefully have some volume of that sample remaining, and you might try rerunning these to make sure that this is a real measurement from the field, not an artifact from your magic analytical box in the laboratory. The other thing I'll point out is this, where I've sort of drawn a plateau down to 0. I call this cutout of a sensor. Sometimes in our field sensors, we lose data. Sometimes they have an automatic ranging where they use either a low range or a high range, depending on concentrations. And when they switch between ranges, you sometimes record some zeros while that's happening. This is also possible if some contaminant touched our sensor or blocked an optical sensor, like a little piece of a leaf got stuck on a light source, you would get back potentially readings of 0. So if we see something that's obviously a sensor failure, we also want to go ahead and remove those data from our analysis. And so what remains is the data set that we'll actually push forward with. Okay, and just to point out again, there are very few hard and fast rules about how to do this or how to standardize it. It's incredibly important to make decisions that are justifiable and that are non-arbitrary. Above all else, document your workflow, document your thinking each time you're making these sorts of corrections, so that others who might use the data set or yourself in a year when you write about it may remember exactly what you've done. All right, so we have a nice clean looking data set now. We know when our injection occurred in orange, and we've got a lot of data here, potentially a lot of background data at early time and late time. And so I'm going to suggest that we do our trimming in two steps. First subjective, then objectively. So subjectively, what I want to do is zoom in on the period that begins at the injection time and ends at this point where the tracer starts to visually move up. We'll zoom in on that point, and what we're going to try to do is define where we think our tracer actually began to appear. Similarly, out in the late time tailing, we'll want to zoom in on that. And I often do this with a log scale on the concentration so you can really see what those fluctuations look like. And in an optimal world, you might get a graph that looks like this one, where that light blue line is sort of a moving average. And what I'll do is try to pick just after that moving average essentially drops off precipitously. And I'm hoping to see that because it means I've measured my tracer quite long in time. It won't always look like this, but it might. So we have a couple of goals here. One is we want to isolate the signal due to our tracer. So if we know it's noise, background prior to our tracer release, for example, or the extremely late time observations, we want to get rid of those. Secondly, best to keep a little more data than over truncate at this step. So I would rather have too much than too little in my time series. Every truncation that we make, we're saying, look, even though a concentration was recorded there, I don't believe my tracer contributed to that. I think that's fluctuation in the background. So we want to make sure we're keeping as much information as we can to help us work through this problem. Now, with that subjective clip done from the previous slide, we're going to go ahead and do what I consider to be a more objective trimming of the data. And this is a strategy that Seth, Kurt Mason, and others have used, and they first did this in the early 2010s, I think in 2012 paper. And the idea is the total mass that we might recover under our breakthrough curve can be calculated by the discharge Q multiplied by the integration of this time series between those 2 points. And what Mason and others said was, well, look, let's say that we all feel pretty confident in the first 99% of this. In other words, the greatest uncertainty comes out here in the tailing. And that attribution was made because the rising limb tends to be much steeper. And so it's actually much, they contend, easier to identify the point at which the rising limb begins to rise. So what they've essentially set up is a strategy where you're trying to find the time at which 99% of the recovered mass has actually come by. They call that T99, and that is the time scale that you want to look for. And I'm noticing in that equation there should have been a black Q in front of it, sorry. So that T99 should be before the objective truncation that you did on the previous slide. By definition, it must be, because 100% of the mass occurs when we get to that time scale, T2. So your goal here is to find that time at which 99% of the signal is to the left and 1% is to the right. And what we're doing then is clipping out that highest uncertainty part after T99. What it leaves us with is this breakthrough curve that I've traced over in dark red, and that's what we'll actually analyze moving forward. One other strategy to do this, if you actually plot mass recovery as a percentage of its total through time, you'll almost certainly get a curve that looks like this. You could do that with a trapezoidal integration of the data set, for example, where the ultimate value here would then be at a value of 1 for 100%. And your T99, you could find the time at which this crosses 0.99, read down, and that will be the T99 that you want to record. So you can solve the equation for it, or you can do it in sort of a graphical method by estimating that cumulative integration. In MATLAB, the cum traps, for example, cum traps is a good function to use, though you can write a trapezoidal integration yourself quite easily. All right, so we've trimmed it subjectively to get rid of what we know was bad or background data. We've trimmed it objectively now to get to this T99 and define the time scale that we're going to analyze. And my final step in the workflow is reproducibility. So we want to document the steps and potentially export and archive the data sets in the most raw form that we have after we've done any conversion, so conductivity to concentration in our example. We want to document the background correction. What number did we use? Did we create any negatives? What was our strategy to deal with negative concentrations? Did we remove any outliers? What was the justification? Was this based on visual inspection? How did we clip the data? So the time scale that we chose early, the time scale that we chose late, the T99 that we calculated. And I cannot emphasize this enough. For reproducibility to work in our field and in our sciences, these have to be documented. Right? If someone is looking at your final, cleaned, corrected, shifted for background, outliers removed data set, that's not the same as looking at your raw data set. And it's very important to document that difference. Hopefully everyone is getting in the habit that as we write manuscripts, as we publish our studies, we're including the data with it as a supplement or storing it in an open data set repository, of which there are many, one example being Quasi's water data center. Okay, so we've executed our field experiment, we've got our data home, we've cleaned it up. You are at the end of this section 2 of this course, and when we come back in section 3, we'll actually start to take these time series and use them to learn about our system. See you all in the next video.